Okay, so first I'll talk a little bit about visualization of spatial data in general. It's very introductory, and after that I'll go a little bit deeper into visualization itself, and then I will say something about TeamMap. Together with Jacob, we have quite some exciting things to show. But first of all, visualization of spatial data. So as you of course already saw, like we have like vector data, which is pretty much covered in the SF package. Well, basic types, points, lines, polygons. Of course, spatial raster data. I'll not go into depth just yet. But of course, what's already covered is the coordinates reference system, especially by Etzer this morning. The point is how, if you want to visualize spatial data, especially on a global scale, you need to think about how to peel an orange. The world is 3D, it's a globe. How to put it on a flat, two-dimensional surface or device. So that's what projected CRSs are for. We need them if we want to visualize data. I mean, we can wait a couple of decades until holograms will be a common use, but until that, we have to do it with flat surfaces. Of course, we have 3D visualization, but even like this orange, even though it's 3D, if you plot it on a flat device, it's still a 2D projection. Of course, you can use projected CRSs for visualization, but be careful because it's still a compromise. Especially when you work with global data, you need to be very careful about the poles, about the 180 degrees longitude and so on. So this is just an overview of the type of projections that we have. And some examples. Let's just for record. So just skip this slide for now. For visualization purposes, doesn't matter. Yes, it does matter. So this is a quite simple example of population density. And the left-hand side map is the web Mercator, which is typically used by Google Maps, etc. And on the right-hand side, a projected CRS that was used in TMAP by default. And that's a good one for world maps. There are others like Robinson, Winkle Triple, etc. Doesn't really matter which one, but you see that that Australia is 3 times as large as Greenland, which is the truth, and not the other way around, like here. For spatial density, it really matters, because otherwise you get like a biased image of where people live. Here is you would expect that many people live in Alaska, where it's not the case. So for statistics, that's what I mentioned here. Are the properties which a projection satisfies or doesn't satisfy. Equal area, so this map projection satisfies the equal area properties. So it means that the area of the polygons are basically the true areas. However, so that therefore it's still compromise. The shapes can be distorted, especially New Zealand. This is more realistic than this one. So depending on the application, so statistics, okay, we say shape doesn't really matter because it's about population density, but for other purposes like geology, it does matter, and navigation, of course. So there we can recommend other projections. Yes, I see a question. Please go ahead, Brian. or otherwise we can wait until after the presentation. It doesn't matter for me. For spatial data in R, there are four. Yeah, I listed here 4 core packages which are basically covered. Terra will be covered after this presentation. There's also quite handy thing in the stars package, which are data cubes, which you probably are familiar with or have seen before. It's very useful both for vector data and for raster data, because you can have different layers which you can use as timestamps, for instance. So you can have a time series analysis, which you can also use to visualize. So far the basic spatial data summary in R. As for the visualization part, so now comes the core of the presentation. This is what I perceive as a good workflow for to create a nice visualization. Of course, you have to start with pre-processing of data, and data, as you know, it has like a content data part. So, for instance, employment, air quality, etc. It basically answers the question, what do we want to visualize? Whereas a spatial data component answers the question, where are those phenomena that you want to visualize? So you need to pre-process, like taking into account missing values, duplicated values, all those things. After that, you join those data, and then you can start the visualization part. And that's also these 2 blocks where tmap comes into play. And other packages as well, of course. But yeah, I'll just cover things that are in tmap after this, the slides. And this basically, so in this block, it's about data-driven spatial transformation. It's an optional block. Not many visualizations have those transformations. However, it will become optional in tmap in the next update. And I'll explain what this is. So when we have spatial data, you can use the content data to change the features. You can, for instance, inflate polygons or deflate polygons, as I will show in the next example. And for that, you need like a variable of interest, some scaling function which scales to the size of polygons, and then apply a certain data-driven spatial transformation. After that, you have like this transformed data that still contains a content part and a spatial data part. And then you need a visual mapping. So this means that you need to map the data variables to the visual variables. Now the visual variables are, these are the most important ones. So colors, well, kind of multiple different type of color palettes, size, shape. Others are alpha transparency, line type, fill pattern, etc. Those are a little bit less common. They're not included into tmap yet, but they will be. I'll talk about that in a second. And then, yeah, here's our spatial object types. So symbols, lines, polygons, and rasters. So basically, you can map a variable to either color palette or symbol size, symbol shape, line width. So line width is basically size, basically this one. And when you have done that, yeah, you can just plot it on a map. And it can be static map, interactive map, etc. That's up to the device, but at least you have the information to create the visualization. So an example of this data-driven transformation function is the cartogram. So you've probably seen it. It's a little bit playful way to visualize, in this case, Happy Planet Index corrected by population density. So what we do here is we distort the polygons such that the areas correspond to population size, and such as neighboring polygons still touch each other. There's also a non-contiguous variant of the cartogram, which polygons just shrink but don't touch each other. In this example, so I used population as a data variable, which I mapped to polygon size as the weights. So population is between 0 and 1 billion, and I use a continuous scale to scale it to 0, 1 units, weights in this case, which then are passed on to the cartogram function. And then I use Happy Planet indicator index. So these numbers are between 10 and 45, but I use intervals because, well, you can use continuous color palette as well, but in this case I choose intervals, which has the advantage that you can really read the value better than a continuous color palette. But these are choices. These are choices that depend on the task, on the user, background of the user, all those things. So in this case, I use a diverging palette, red, yellow, green. This looks pretty nice. However, I've been told that this color palette does not work very well for colorblind people. So therefore, in the next major team map update, we switch to another default. We haven't decided which one, but at least we want to take into account those people because there are many of them. So this goes a little deeper into visualization itself. So visualization is all about losing information. We often want to visualize all information because you don't want to lose any information. Maybe it's important, so we're really afraid of losing information. However, big data, spatial data in general, is often very detailed. And for many user tasks, this high level of detail is not needed. So if you want to visualize for instance, like climate change on a global scale, you don't need to know that some kind of neighborhood in some city had like a very high temperature at some point of the day, just to give an example. Then it's probably better to use some kind of kernel density smoothing to visualize the global patterns. So information loss is therefore key concept in good visual design. You can think about how to lose some information, but on the same side of the other side of the same coin is the goal of visual design is to find the best way to depict some information. So that's basically the question is, what information do you want to visualize? It's the same question as what information could you get rid of? So for instance, the underground map. So the question is realistic always better? So the underground map is not realistic. So these are realistic locations. However, often people find these maps to be very useful. Why is that? Because of the population density. The population density in London city center is much higher. Therefore, the metro stops are closer to each other, and as a result, you can print the labels better. You need very small font size. Also, the directions here we also use like 8 cardinal directions. In reality, it's much more organic, I would say. but due to this schematic way of visualization, it's easier, to digest this load of information. So you need to think about. So this is also maybe it's also a case of data-driven spatial information, where you use population density to move the points, the underground stops in this case, a little bit farther from each other in order to be useful for public transport planning. So we use this. So these concepts of information loss are borrowed from information theory. And I've been in Oxford for half a year, and then I worked together with Professor Min Chen, and we focused on a design space for origin destination data visualization. So here's the reference. And in this case, we composed of 4 dimensions. So this design space consists of 4 dimensions. And the first 2 dimensions cover like the data structure of the nodes and edges. And the third and the fourth, the visual variables. So basically how to depict them. This is just an example of applying these concepts of information loss to a specific type of spatial data, namely origin destination data visualization. And when we worked on that, we kind of saw a new design emerging, because I had this data set of Dutch commuting, which basically described how many people commuted from one municipality to the other. And eventually we designed this map. So it's called the donut map. Let me show you. Let's see. It's here. So I can put the URL in the chat to everyone. There you go. It may be a little bit slow because of the Zoom link, but well, it's okay. So what we basically did is instead of whole lines, so we draw half lines. This means that the flows between Utrecht and Amsterdam can be depicted by 2 half lines, which together form a whole line. I've been told that's also Gestalt theory, that's the underlying core principles behind it. In this case, the pink lines are the commuting flows of people who work in Amsterdam, and the green ones who work in Utrecht. And the donuts summarize where the people who live in Amsterdam work, and the majority work also in Amsterdam. And you can see the commuting towns where they work. So a lot of commuter towns have people who work in Amsterdam because of these pink parts. Many people here work in The Hague, so it's a little bit trivial, but and the interesting thing is for policymakers, it can be really interesting because they can find out whether it's about the number of jobs that's available because so many people commute, or because it has a good public transport system, or on the other hand, not so good. So they can like create infrastructure based on these data. So back to the presentation again. So visualization of spatial data in R. This is kind of an overview. It's probably not complete, but as far as I know, these are all great packages to visualize spatial data. Well, the plot function is fast and straightforward, so it's implemented in every like class package, SF star, Stera, etc. Usually is the fastest way to plot data. ggplot2, it's really great. In the past, it was little bit lagging behind because it's not suited for spatial data, but today it is. So TMAP, yeah, we started, I think, a couple of years ago, 6 years ago, and it's maturing. It's mature right now, and currently we are, as I will talk in the next slide, have plans for a major update. MapView package is also really great. So both TMap and MapView are built on top of Leaflet. So Leaflet is used, it's a JavaScript library for interactive maps. And so TMap has two kind of modes, two devices. So the static device, which you use, which you see in RStudio, and the plot device, the view device, view pane, in which you can see interactive maps. And these interactive maps, yeah, we are using Leaflet as a fundamental package for that. MapSF also looks really nice. Haven't used it before, but very promising. But now about TMap. This is the news I want to share. So as I said, the current version is pretty stable, pretty mature. Of course, there can be bugs anytime, as with any software. But it's kind of grown to its full potential. However, we had trouble in extending it. So therefore, we had to develop a new framework. So for the user, a little bit, some things will change, but the core concepts will, of course, be the same. But it can be much easier. It will be much easier to extend it. And the next news I want to share is that we are going to publish a book. So me and Jacob Novstad. The draft version is already online. It's over here. And it basically covers, so we completed about half of it, probably a little bit more, but at least the fundamental things that you need for TMap. Spatial data in R, this is more general. TMap in a nutshell, it's really, if you want a quick overview what TMap does, you can read this chapter. Basically, you can go through it very briefly, just an eye overview. QTM, so if you have a spatial data object, no matter what class, you can plot it with quick thematic map. In this case, volcanoes. Let me close my email for a second. Okay. And so if you plot it in the tmap way, which is, if you're familiar with ggplot, kind of similar, but it has some things that's done a little bit differently. So what's, instead of ggplot data set and then the aesthetics, we use tm shape. So tm shape is used to like specify what I call a shape object. It's a spatial object, can be an SF data frame, stars object, Terra, other things. And then we have like the map layers. So these are TM symbols, TM polygons, lines, and TM raster. These are the basic ones. TM text. And then you can specify aesthetics, which means the visual variables. And this TM symbol has 3: color, shape, size. In this case, we keep the shape constant and we use a data variable to be mapped to the size visual variable. In this case, so elevation. Elevation comes from volcanoes, and we have a title. Let's see if this map is there. This is this map. So apparently 24 is triangles, and elevation is used. So here's a legend. It's scaled to elevation. And so on and so forth. So yeah, as you can see here, you can design the map any way you want. So like background colors, you use a continuous scale for elevation. So it's supposed to be a really flexible package. So here's some map attributes like scale bar, compass, etc. See how much I'm on time. Okay. Yeah, so I said we have the plot and view mode. So I can show little quick demo. So I have the world data set, so data world. And if I go TM shape world, TM polygons HPI, I have the happy planet index. And if I use, let's do it here, team map mode, view, and then I can rerun this code, and then I'm in view mode. That means interactive mode. This all thanks to Leaflet, the people who contributed to Leaflet, what made it possible. Again, for statistical mapping, it's not really great because what I said earlier, Greenland is still 3 times as large as Australia. But other than that, it's very neat that you can zoom in and zoom out. And so back to the book again. Yeah, not all paragraphs have been written yet, but I think the core is there. So in this book, we'll cover like how to specify spatial data, like with the TM shape function. The chapter 5 is about layers. So these are the base layers and the derived layers. These are the visual variables you can use, and the geometry that it expects, which means that it can take more geometry. So for instance, TM polygons can also take TM the other way around. TM symbols can also take polygons. Then just the centroid is taken. And if you, for instance, use multiple shapes in multiple projections, then it's automatically, so this is all described, by the way, in the previous chapter, then it uses the CRS of one shape, which you can later on change. So chapter 5, chapter 5 was about layers, chapter 6 about visual variables. You've seen this picture before. To dive a little bit deeper, yes, so other types, so these are not written yet, so layout is written, it's already finished. So you can use different font size, etc. So please let me know if there are any questions or suggestions. We're open to that. As I mentioned in the slide, so this book is written for TMAP 3 and will be updated to TMAP 4 because there are quite some changes in TMAP 4, which I want to present now. So TMAP 4, the major thing is that it will be extendable. And it's extendable in many ways. We can add map layers, or by we I mean developers, other than me, who wrote basically the framework of TMAP, but anyone who is familiar into R can add map layers. You can think about TM donuts, like the donut map that I showed, TM hexagons, TM network. So for instance, if you have like an SF networks object and you want to visualize it straight away, why not use TM network? We have to, of course, think about how to use it and what kind of aesthetics you have, etc. But sky's the limit in this case. TM Hillshade. There could be many more, like TM kernel density estimation. Aesthetics, so there will be many more visual variables available. So we have added five new aesthetics for TM polygons. And again, it will be relatively easy for developers to add new visual variables. Once you have like a method to plot them, it's also easy to add them. So the graphics engine, so TM3 had two plot modes. Plot, which basically is built upon the grid graphic system, and view, built upon leaflet. But if there is another plotting mechanism, graphics engine that could be used, why not use it? And finally, spatial class we use is built upon SF and stars, but it will be also more easy to incorporate other classes as well. So for instance, the Terra classes. So a small example of the aesthetics. So just to show the pictures, it's easier. So this was basically, this about syntax. The syntax will change too, because there are many arguments. If you look at TM symbols, for instance, they are like a huge list because we have 3 aesthetics, and every aesthetic has a bunch of arguments. In TMF4, it will be organized in this way that an aesthetic still is an aesthetic fill. The scaling arguments are bundled into a scale function, in this case TM scale intervals, and the things that only are related to legend is configured in TM legend. So for instance, the title. This is an example of 3 different aesthetics. So we use, as you can see, I've improved the continuous legend here. Still have to implement the landscape legend, but so border width and line type. So in this case, border type is life expectancy. So dashed means a little bit earlier in life. Unfortunately, thicker. Or no, the solid lines means a little bit later. Well-being, thickness of the lines, and happy planet index is color. So in this case, best to live in Middle and South America. Map layers. So the cartogram that which you already saw. And this, by the way, is an example of a diverging color palette which takes into account color blindness. So it's used as a transformation aesthetic. So it's basically distorts the polygons such as the areas correspond to the number of people who live in the countries. The code is here. I'll not go into detail. You can see again the aesthetics are remain the same, and the scale arguments are bundled in the scale functions. And scale functions are summarized over here. So I currently have these ones. Doesn't mean it changes, but can mean we probably we add a couple of more. So for instance, date, time are not included yet, but I will include them. These are the main data types that are expected. So, and you see the differences in this map. So it's the happy planet index or life expectancy. Let's check life expectancy in Africa using 6 different scales. Categorical, every unique value has its own color, and the colors are repeated because we don't have enough colors. Not very useful in this case. Intervals, very useful, because you have a sequential palette. And you can really read the categories. So this orange is this one, 60 to 65. A log scale for this type of data is not very useful. Could be useful for population density or for income, economic data, but not for life expectancy. TM scale ordinal is also a categorical variant. So this is class vector, this is class ordered. Also here every unique value has its own value, but it's also not very useful because this scale is not equidistant. So for instance 53 is missing. And so the continuous scale is also very useful. It gives a better image than this one. But the values are a little bit more difficult to read from the legend. So these have pros and cons, but these are both very useful. TM scale discrete, this is new in TMAP. It basically has a discrete numeric scale. In this case, I'm not sure how valuable it is because there are many values, but if you have like 5 or 6 values and there is one missing, then you still have an equidistant scale. So this will be very useful for that. Multivariate scales. So we can, for an aesthetic, we can assign multiple variables. So in this case, I have a bivariate choropleth. I still have to design the legend, but this is like a concept. In this case, we have like 3 classes, well-being and footprint. And you see that, for instance, North America has a high footprint and a high well-being, whereas Europe, medium footprint, high well-being. So it's pretty easy to read the values and you have like a bivariate choropleth. In TMAP 4, the way it's implemented is by using this MV, stands for multivariate. If you have suggestions for other function name, for another function name, please let me know. But I want to keep it short and tidy. So for now, I've called it MV. So the first variable which defines the rows is well-being. The second, footprint. I have a scale, TM scale bivariate. And I can, for both the rows and columns, assign a scale function, in this case intervals. And the values are a bivariate color palette. I'll talk about color palettes a little bit later. For now, so this TM donut, the donut map that I showed, it's not, so this one is not implemented yet, but it probably will implement it like this. This one is also not implemented, and I'm not sure exactly how to create this map. And also not know what kind of extension libraries we're going to make for that. But I think using SF would be great. And like this, for instance, TM shape edges, or maybe TM shape network, and then TM half lines, TM donuts, and here again, so size, it corresponds to the number of employees who live in the specific municipality. And the parts, the donuts, is also a multivariate thing. It's basically a symbol, and the content of the symbol is a donut chart, and we need to have the number of employees who work in the highlighted municipalities in this case. So it's again an MV function. A legend, so the legend positioning will be different. Will be more options to give them both inside, outside the map. You can specify it per aesthetic. So each aesthetic will have its own legend argument, which you can specify in different ways. In all TMAP, all legends need to go into one position. Also, what's also new is, let's see, this is not, I'm not sure what I was going to show here. Oh yeah, we'll also have like shortcuts like TM place legends left. So I plan to, so the options will be a little bit more complex because the framework is more complex. But we plan to have like a couple of like magic functions that does it all in one function call. And the nice thing about TMap 4 is that, let me show that, is that you can use auto-completion for that. So if you do tm place legends, then you can just place them right. And then you have just to specify the width, 0.2. Let me see if this works. Yeah, it works. So etc. So yeah, those things are really useful. Again, if so, this is really development version. A lot of things don't work yet. If it will be more mature, I will ask you, all of you, to give us feedback of what kind of functions you need. Are the argument names intuitive, etc. So what's also new, I've had this question a couple of times, whether people could make this kind of legend. So we use two aesthetics, symbol size and symbol color, and one legend. So basically, the same data variable is mapped to two visual variables. And now we can say TM legend combine. So the size legend will be combined with fill legend. And one of the last things I want to show this a little bit more. So there is like a free argument, which decides whether facets, the scales of the legends are free, so per facet, or shared among facets. What's new is that can also be done for a facet grid per row per column. So this is kind of a theoretical example. Let me see what I have here. Income group over here. The rows and the columns is economy. Life expectancy for the fill, it's determined per column. So therefore columns is true. And I have the legends for the red symbols, and red symbols are GDP, and it's determined per row. So yeah, that's a new feature. I'm not sure how much it gets used, but at least it's there. So for the backwards compatibility, yeah, it will be backwards compatible. The options will be different because for instance, we want to take into account colorblind people, etc. However, there will be a style called, as I see it now, TMap v3, which reverts everything to the current set of options. So the color palettes. So let me show that here. So I have a function. It's basically the comparable to the palette explorer, which was in TMap tools. Fortunately, I'm on Windows, so installation gets a little bit quicker. Okay. It just renders a large PNG and opens it in a viewer, so you can browse through the palettes. What I plan to use is have it as an HTML format so that you can copy paste the palette names, because they could be very long. But as you see, so we've not decided how to organize these. So far it's been organized as categorical palettes, sequential palettes, diverging palettes, and cyclic palettes, bivariate palettes. And you see here the family. So I have like the Covesi, Carto, Brewer palettes, Ocean, HCl. So both HCl and let me start at the beginning. Yeah, HCl palettes are base R packages palettes. We still haven't decided on the default, but yeah, I think that's all I wanted to show. Let me see. Yeah, so suggestions are welcome. So I have the GitHub page. there's this yellow tmap v4 sign tag that you can use.
We have a lot of questions.
Yeah. Okay.
And it's just yeah, it's a good time to stop. So Hannah, please.
Yeah. All right. Thanks a lot, Martijn. I collected the questions on MetaMost and
there's a lot of questions. So Martijn, please just try to go fast.
Exactly. And the questions that I will not be able to answer, I will answer online.
Yeah. Great. So the first question is, can you please reflect on geemap.org? That's a question from Tom. And how can our community catch up with cloud-based solutions to visualize data?
Say again, Joy?
Or maybe Tom wants to ask the question.
They made a package to work with Google Earth. Yeah, it's called geemap. So how do we catch up with that? Because you can visualize also really large data sets. And
yeah, I think it has both pros and cons. I mean, the great thing is about the R spatial community is that everything is open source, everything is connected, everything is possible. How do we catch up? I don't know. Maybe we can kind of have an interface to that. So I've seen it, but not used it myself. So
okay,
that's a good question. Yeah.
Okay. The second question: would you say TM shape is suitable for plotting high-resolution data as well, or is it recommended always to aggregate data before using TMap?
That's a very good point. There's in TMap shape. Let's see how I go. Probably there's something in the. So there are a couple of options. So data simplification. We have a simplify argument, which you can set to simplify polygons. For rasters, we can. I'm not sure if it's in this chapter, but we have like a max raster option, which is set to say I think 1 million. Which automatically downsamples spatial rasters because you cannot really see more pixels on that. So it's basically done automatically. And I have to say, stars, it's really fast. So yes.
Okay, then probably a related question: does TMap also handle the use of satellite images as base maps?
Yes. So that's a good one. It should be. It should be. So we can, of course, use that as if there's a tile server of satellite images, we can use it, of course. Yeah, then we can use this base map. So I still have to implement base maps for static or for the plot mode because it's not there yet. You still have to use, for instance, map tiles to download the tiles and or the satellite images, and then you can use TM raster, TM RGB. But it's better, yeah, to have it as a base layer.
Right. Next question: can TMap be used to export to KML to be opened in Google Earth or similar?
It's a good question. I've also asked the question one time, whereas TMap, the maps can be exported to ArcGIS, for instance. It's a little bit harder, I guess. For KML, I can imagine that it's possible. And that's not too hard, but it depends on the map. I mean, if you have like a really complex map, then it's a little bit harder, I think, to create an export function.
But you can always make a PNG as a ground overlay, and just put it.
That's always possible, yeah, exactly.
But that would be pity to lose the vector structures, So yeah.
You can probably also export it to SVG, which even more, even better.
Okay, and next question is from Gerard. Do you want to ask it yourself or shall I read it?
You can do that, Hannah.
Okay, so the question is, wait, no, I have to split it, yeah. Do you have any experience with visualization of uncertainty in spatial data?
I've thought about it, but not. It's a really interesting one. You can map uncertainty to a visual variable. So say alpha transparency. As you have to be careful about the color palette. But if the color palette is, for instance, one from Viridis. So let's take one. Which falls, for instance, this one, or the HCL palettes, which are have same brightness, more or less, and then you can use alpha transparency to decode uncertainty. So the brighter the color, the more uncertainty there is. That could be an idea, but I think it's also depending on the use case. And
yeah, thank you, Martijn. I think Tom did something similar in the past with whiteness blurring or something like that.
Yeah, that's kind of similar indeed. Yeah, maybe you can also use the line type. So what I showed in the vignette. Is the vignette here? Something like this that you kind of, yeah, I'm not sure yet. There's also a nice one. The City University of London, they create sketchy graphics. If you have like a polygon, you can use the exact borders, but you can also like sketch it a little bit. Also indicates. So they use it, for instance, for bar charts. If like preliminary results, then you can just sketch a bar chart as if it's written by pencil. Maybe that could be used as well.
Right. Currently, the last question on Overleaf is if you can add something like histograms of classes or values into the legend of TMAP. There's an example of how that should look like included in MetaMost.
Yes, there's a TMAP. Let me use Google for that. It was possible on TMAP 3. So there was like, yeah, for instance, this one. So yeah, at the time, a couple of years ago, I just made like this histogram. For TMAP 4, we have to think about it because I want it to be general as possible. But for sure, we plan to do that. And not just histograms, just any chart which can aid the analysis. And also, I've also asked the question, whereas it could be possible if you have like an interactive map, if you zoom on it, you can show it. Ideally, you want to show it in the pop-up. In many cases, it will be useful.
Let me thank everyone for participating,
please.
and also the summer school participants for bringing up questions. That was very nice, very helpful.
It was a very special